Hello? Oh, I haven't been writing contests for a while, so today not only do I participate in what? In AtCoder beginner contest, but also I try to remember how to code actually. Let's try to register. My God. If you see this, I bought a new camera, so I hope this time it works. Okay. Unrated. Uh, is this about not using ChatGPT? Funny. Okay. We don't have much time for this. So let's check that it at least compiles. Because I have a long template and maybe AtCoder won't be able to process it. Okay, it at least compiles it. Okay, let's see the problems. Oh, I forgot about my tablet. Okay, later. I will turn it on later. What is that? How do you give such problems? What else should I read? K and N? So, what do I need to do? Ah, X as well. Sorry. So I need to insert plus what? So immediately after the kth element. So it's like K, and then I need to write what I want to insert X. Yes. Let's see. So it failed to insert something. K is 7, N is 3. Why? Ah, I don't need to read it. Let's submit this. Intersection of cuboids. C ABCDF is a cuboid with a diagonal connecting this. Okay, I need to read 12 numbers. Can I read it in int? Yeah. So if dot read vi return false. Okay, so what do I need to check? Yes or no? Yeah, yes or no. So if I need to write so if a maximum of vi and vi plus 6 is greater or equal than maximum of vi plus 3 and vi plus 9, actually minimum, then answer is false. Answer becomes false. Copy, copy, and copy. So we need yes, no, yes, I guess. Excellent. Did I manage to read all 12 numbers? Probably yes. Problem C. We're given a sequence A of length n. Freely choose exactly k from A and remove them, then concatenate the remaining elements in their original order to form a new sequence B. Find the minimum possible value of this. The maximum value of B minus the minimum value of B. So obviously we either need to remove No. We need to sort, of course, and we need to remove several beginning elements and several ending elements. Great. So VVI VN, read V, and print find dance of V. Good. So what do we need here? We need to return here int. Here we need to sort whole A, and then we need to not only do we need, we also need K. So K is the number of removed elements, as far as I know. So we sort whole A, and we need, so how many options do we have? So if we need to remove one element, there are two options. Okay, so 1 and 9 is fine. Yes. So answer is minimum of answer, and what? So we try to subtract A for example like this. Yeah. So for example, if I equals 0, then we removed nothing from the end. But then we need to remove k elements from the beginning. So like this. Good. Yeah, this is probably it. 2018. Perfect. It's sad, but we need to agree that actually ChatGPT would be faster than me. So humans already lost some of the battles in competitive programming. N+2 cells arranged in a row. Let cell I denote the ith cell from the left. In each cell from, okay, I think it's time when we need actual tablet. Good. Good. Actually, tablet does not work. Ah, it works. Okay. So we have a line of length n+2, and in each of the cells there is a stone. Let's see what next. For each from cell 1 to cell n. Yeah, so nothing here and here. Oh well. Also there is a string, yeah, and we have initial colors of stones. So we can choose a pair of adjacent cells that both contain stones and move these two stones to the empty two cells while preserving their order. Wow. Actually, this is something. Actually, this is just BFS, I guess. Yeah. Probably this is just BFS. So we need to read a string S and T. Yeah. So we say that vi is si equals example black, and wi is ti equals black. Okay. And then we need to return the minimum number of actions. So find ans of v and w. Okay. So how do we approach this problem? So actually our state is, first of all, a mask and the position of two empty elements. This is our state. And we need to make, also let's make something for okay, never mind. State is a state. Yeah. So let's make a starting state. And the finishing state. So v dot e. Let's also make n. And initially this n and this is n. And this is done. Okay, so we have two states. Then we need to make some transitions. So we need to make some transitions. How do we make some transitions? So we take u of states, we push their v, and also we want vvi distances of n plus 1 and this number, I guess. And initially it's filled with minus ones. So it should be So I have like a million integers. This is 4 megabytes, which is fine. Yeah. And I say that distance of v.e v.mask is 0. Then let's say that while not q.empty. So what do? I say I have state current equals q.prompt, q.pop. Then I need to iterate over all possible next states. So what do I say here? I say that if absolute value of difference between I and current dot e is less than 2, then continue. Then I need to swap it. How do I swap it? So I take the mask of these 2 elements. So par.mask move by I and then taken 3. Then I need to from NXT mask I need to remove this U, and then I need to add it to the missing place. And it follows that I need to replace nxt.e with I. Okay, then I need to say that if a distance of nxt.e nxt.mask is at least 0, then continue. Otherwise, I need to push it into the queue and say that this distance is 1 plus the distance this one. Good. Then I need to return distance of w.e w.mask. So we have 4 minus 1 and 7. Ah, do like this. Thank you, Visual Studio. Thank you, Visual Studio. Okay, I forgot to print this. But actually the answers are fine. Yeah? 4 minus 1, 7. Good enough. Accepted in 7 milliseconds. I expected more. Like at least 100 milliseconds maybe. At least 10. In the nation of AtCoder, there are n cities from 1 to n and n minus 1 roads. So we have a tree, a weighted tree. Find the minimum travel distance required to start from a city and visit all cities at least one using the roads. This is very standard problem. You just need to add all numbers and subtract the maximum one. Add all numbers. No. add all numbers twice and subtract the diameter of this tree. This is the solution. So, okay, n, and then a lot of edges. Good. So I have read it. And then I need to simply find answer of E. Yeah. So what do we do here? First of all, we need to find the diameter of the graph. And how to do that? We need to find all distances. Actually, we will need long longs, unfortunately, for that. Find distances. So we need a graph. We need the matrix of all edges, of the lengths of the edges. And basically we need the starting reference. So if we have this function, then everything is easier. So we say VLD is find distance from 0. Then we need to take the maximum number in this array. And then we again need to find distance of GHX. Then we need to find the max element in this array. This time actually we just need the diameter. So we need this max element. So this is the diameter. What was that? Actually long. Then we take minus diam, and then we need to add up all edges. Good. So actually we only need to fill GH and find dist. So we say that gf dot a dot pushback f dot b and h f dot a dot pushback f dot c, and conversely g f dot b dot pushback f dot a and h f dot b dot pushback f dot c. Good. Okay, we have filled g and h. So how do we find the distance? For all distances from V. So we need to create an array. Let's fill it with -1s initially. Also, let's say that dst of V is 0. Then we need to run DFS. gh v ghdst and return dst. So what does DFS do? So dst says that let's go through all neighbor index. So let's say 2 is G, V, and I. So if it is already visited, so dst2 is at least 0, and then continue. Otherwise, we need to say that dst2 can be calculated as dstv plus the length of the edge, which is hvni. After that, we need to run dfs of 2ghdst. So 11 and 9 billion. Oh no, somewhere I failed to use long longs. This is not a good sign because I expected. Oh. $11 and 9 billion. Great. These bugs with ints and long longs is very sneaky. Sometimes. Problem E. The nation of AtCoder. I failed to understand that E is already solved, so we need only F and G. F minus x is a to the power b. How many integers x between 1 and n can be expressed as x equals a to the power b using some positive integer a and a positive integer b not less than 2? Okay. Not very hard. So integer n, read n, return false. So what do I do here? Well, actually, what do I do here? Well, the problem is not very hard, but unfortunately it might require doubles, which I don't want. Not doubles, but int 128, which I don't want. So let's avoid it. Also, I kinda dislike that find us n. Ah, I need some exclusion inclusion and some Möbius function maybe. Okay, let's make it long, although it's probably int. Okay, so first of all, we need some basic function which says how many exact kth powers are there. First of all, and secondly, we always ignore one. So in all functions, one will be ignored because one is a mess, actually. So let's just say that we calculate something and in the end, we return ans plus 1, simply. Yeah, okay, so first of all, if k is at least n, we simply return 0. No, if k is at least 61, we simply return 0 because there are no such numbers. Even 60 would be nice. Then I suggest the following. So let's take the power of n to the power to the power of 1 over k. Yes. Then actually let's take its ceiling, and actually it should be int. Let's make it long. Okay, also if k is 1, probably we need to just take n minus 1. So d is ceiling of this number. Yeah, so while power d to the power k is greater than n times 1.1, for example, we need to subtract 1 from d. And then when integers are fine, we can switch to integer powers. Okay, actually, I want it like this. It's really strange that there are some weird overloads that I know nothing about. Okay, now we need some integer power. Do I have an integer power function? No. So I say now actually almost the same, but instead of power I use int power, and instead of greater than n times 1.1 I simply use greater than n. Okay, now int power decay is at most n, and this is actually great because I can return d minus 1. Okay, basic counts is done. Now we need to somehow calculate the answer. So I need to take the answer for 2, for example, then for 3, but then I need to subtract the answer for 6. For 6 because it is like here and it is calculated twice. And generally I need to use my Mobius function, I guess. So what do we do? What do we do? What do we do? I think we just calculate the Mobius function for all numbers from 1 to 300, 3600. So minimum prime of size C and Mobius function also of size C. Okay, let's go. So we need to write an Eratosthenes sieve. So first of all, if minimum prime of I is also I will calculate minus Mobius function. Actually, I will calculate minus Mobius function. Let's see here 1. So if mi is zero, then mi is I, and the Mobius function is correct because it is 1. Otherwise, I need to say that I take mi, I need to divide I by mi, and if it is still divisible by mi, then Mobius function is 0. Else the Mobius function of I is calculated as minus Mobius function of I divided by mi. Then I need to go through also I need primes. So let's go through all primes. So what do we do here? So we try to multiply I by all primes. So first of all, if P is greater than minimum prime of I, then break. If P, so int Q is I times P, so if Q is greater than mi, then we also break. No, if Q is at least C, then we also break. Otherwise, we say that minimum prime of Q is P. That's it. Then we need to go through all i's here, and we need to say that so if Mobius I is 0, then continue. Otherwise, sum plus equals Mobius of I times find basic cons of n and I. Okay, probably it won't work because it was a mess. It was really a mess. $12 and some correct number. What did I do? And finally, problem G, if this does not fail. It still didn't fail. Problem G. There are n stones on a two-dimensional plane. The ith stone is located at coordinates x, y, y, y. All stones are located at lattice points in the first quadrant, so x and y are at least 0. Count the number of lattice points x, y where no stone is placed, and it is impossible to reach -1 from x, y by repeatedly moving up, down, left, and right without passing through coordinates where a stone is placed. Wow. Wow, this is a hard problem. I don't have any idea how to do it. Did people already solve it? Of course they did, because I was really slow for these problems. Why do I have some sort of military rank? This looks strange. Okay, but what? And Turi solved it in, in 9 minutes. In 9 minutes did he solve this problem. What? Well, this is some royal pain. Why doesn't it work? What's wrong with this? What's wrong with this? It doesn't work. Okay, whatever. So we want to reach this point, but actually I would like to point out that we want to reach this point, because if we reach this point somehow, so plus infinity, if we can reach, then we can eventually go here and then here. So so actually we want to find the number of points for which this is unreachable. Okay. So how do we do it? How do we approach this problem? Oh my god. Okay, let's do something with it. So first of let's take some let's take some point. So if we go up, at some moment we go to plus infinity. So if it is possible, then actually this point is free. So the only way it can be blocked is if there is a stone here. So for each point which is blocked, there is a point in its column. So let's iterate over all columns in which there is at least one stone. And only there can be interesting points. Moreover, all these stones divide this column into several segments, and we just want to calculate for each segment if it is blocked or not. And if we do that, then we just need to sum the lengths of these blocks, of the blocked blocks. So now the question, how do we do it? And to do that, I think we need to do some sort of DFS maybe. So first of all, we can understand that some point is free. Okay. Hmm. Hmm. What is happening? Okay, actually, so we have several segments here and several segments here. So let's say that they are intersecting if there is like a domino like this. Actually, the number of edges will be linear. Yeah, it will be linear just because, well, it cannot be very big. So therefore, we can just construct this whole graph. Oh, this is awful, but fine. This is awful, but fine. Also the coordinates are not very big. It's nice. Okay, let's go. Let's probably go. Oh, but I dislike it. I really dislike it. So we need to read n. This is the number of stones. Then we need to read the coordinates. Then we need to calculate the answer. And actually maybe it is long. Okay. how do we find this answer? So again, how I see this. For each column, we make the subdivision into segments. Okay, so let's do it like this. So we have vector of set of int. So for each fixed x coordinate, which y coordinates are filled. And then I go through v, and I say that field p dot x insert p dot y. Okay. Okay, now for each stone except the maximum one. Oh, I hate this. Why do you always break such an easy app? Okay, for each column, for each stone, the column of empty cells above this cell is a vertex. So I have many vertices. Okay, let's go. Column from 0. Actually, there is also minus first column, which is empty, and there is... Okay, let's say that I want to visit. Let's add 1 to all coordinates, I think. Let's add 1 to all coordinates. Okay, after that, after I have done this, they are from 1 to this number. So actually I can write like this. So they are all at most this number, so they are all less than this number. But I write this because I also want an empty frame around this thing. Okay, let's compare Cth and C plus first columns. Ah, I don't want it like this. I want vector of ints. But then I want to sort it. Okay. Now I consider two consecutive columns. And I want something like 2 pointers. I want something like 2 pointers. And I want to add edges. I want to add edges. So let's also create some vector of numbers of the vertices. So vertex number of size c. This is actually, if I take the lowest stone in ith column, what is the number of vertex above it? So vertex number in the cth column can be calculated as vertex number in c minus first column plus the number of vertices in c minus first column, which is field c minus 1 dot size. Okay. Okay. Also, I want... Actually, let's do it like this. And like this. Okay, now vn.back is the total number of vertices. Let's call it v, which is vn.back. This is the total number of vertices. And then now I want to start constructing my graph. So for each vertex, I want to know its size and is it free or not. So first of all, is it free or not? Initially, everything is not free. And what? And its length. Let's go again through all vertices, through all columns. So initially, so if field C empty, continue. Otherwise, I need to say that I take the vertex number of the next column, subtract 1, and this is definitely free. For all other vertices, I need to calculate their length. So what do? I say length of vnc plus I is equal to field ci plus 1 minus field ci minus 1. Okay, this is their length. Good. Now I need to make this I need to create a graph. Something like edges. I need to fill it with edges. What will I do next? After that, I will say that I have VIG of size V. I need to fill it with my edges. And then I need to run DFS. So then I need to... What do I need to do actually? Ah, okay. So let's say visited of size V, which is initially false. And I will have my function DFS, which returns, so in this connected component, how many unfree vertices are there. So if already visited I, then continue. Then I need to say that ans plus equals DFS of I visited G L and free. Actually, DFS will return pair of bool and ll. So bool returns, bool is true. Bool is true. Bool is true if actually I don't want it like this. No, I don't want it like this. Of what I want, is I want to propagate the state of being free to all vertices which are reachable. So DFS simply runs like this. So starting with vertex, if this vertex is free, it propagates to all reachable vertices the fact that it is free. So how does it do it? So it says that fr, also I need visited. Also I need visited. So simply visited vis of v is true. Also fr of v is true. And if its neighbor was not visited, then we run DFS of 2G FR vis. Okay, and finally, so if a vertex is still not free, then we have to add the length of this vertex to the answer. Good. So actually we only need this thing. We need to create a graph. And this is the hardest part, I believe. Okay, so let's keep track of the last seen stone. Last seen stone. So for example, here it is minus like 5, and here it is also minus 5. Then we take the following stone here and here and take the lowest one. Now we have two segments. Which may or may not intersect. Okay. So let's write it somehow. So we have in the left column we have small number and big number. And in the right column we have small number and a big number. And we have something like the number of the current stone. Current left is -1 and current right is also -1. Now what do we do? While current left. So what I want actually -2. While current left is let me think. Field c.size. Okay, if I have two stones, then I stop when both of them are ones. Then I stop when both of them are ones. Okay, I'm here. So we need to increase something. So we have two segments. We have two segments. Probably. So if LB is less than RB, then we want to increase the left one. Otherwise, we want to increase the right one. Okay, here we want to increase the left one. So how do we increase the left one? We say that CL is increased. Now L small is actually L big. And we want to say that L big is now field C CL plus 1. Not CL plus 1. Yes, CL plus 1. How does tourist do it in 9 minutes? I don't understand, but whatever. Okay, so we have CL plus 1 segment, this segment. Okay, so what next? What do we do when we have such a segment? When we have such a segment, we want to find this number. So we know that CL plus 1, actually we know that CL should be less than CL should be less one than this number. I need write like this maybe. Okay, so here we want to do it only if this is true. Otherwise, we want to use some sort of infinity like this. Okay, otherwise we want the same thing here. Plus plus CR. Right S is right big. Right big is current right this. Yes. Okay, now if so what do we want? So first of all, if some of them is empty, we want to skip. So if LB minus LS is 1, we continue. If right B minus right small is 1, then continue. Also, if they don't intersect, we want to continue. So if left small turned out to be at least right B, even right B minus 1 actually, we continue. And if right small is at least L big minus 1 will also continue. Okay, otherwise these segments definitely intersect. If we avoided all of this, they definitely intersect. So if left is free, so free, how is it done? VNC plus current left. So then we say VNC plus 1 plus current right. And then both of them should be true. Ah, no. Instead of that, I just add an edge. I need to add an edge. So how do I add an edge? I say that E dot in place back this and this. Good. This is good. Probably that's it. Now we only need to guarantee that it works somehow. -1, -1. How did it happen? No. Why did it happen? Ah, actually, if one of them is negative. Yeah. Yeah, I see. So actually, we need to make some. We need to edit it a bit. So if CL is negative, or CR is negative, then we don't want to do it. So if CL is at least 0, we say that free of this is true. If CR is at least 0, then this is free. And only else we push this edge. One. Interesting. However, I don't understand why it was. Ah, it was so slow because of debug. Yeah. Yeah, it's fine. Oh, sorry. For some reason I opened LaTeX. 102. So 2 is incorrect. It should be 6. Why did it happen? Let's make something easier. Like 6 1 0 0 1 0 2 1 3 2 1 2 2. So it says 1. However, it shouldn't have said 1 because I just drew this picture. Most obviously, it should be okay. Let's see what happened. Ah, because L. Actually, for some reason, I counted not what I needed. 2.6. Okay, this time it worked. Let's just submit because I'm tired. Maybe it'll say that I have wrong answer, but at least on samples it is okay. Wow. Okay, that was enough for me. That was enough. 44th place. Okay, let's go. Okay, so you see, I spent 40 minutes on this problem. And Tori spent 9. Like, what? Guys. Hino239 also spent 9 minutes. 11 minutes. 14 minutes. How do they do it? I actually would like to understand. Actually would like to understand. ISAF27, what? Well, so probably I'll make some short explanations of all problems. Okay, problem A. So you're given an integer sequence A of length n and integers k and x. We need to insert x immediately after the kth element of A. So you can do it just with some cycles. Yeah, for example, if you have a sequence A and you need to insert x exactly after kth element, then you can, for example, write a0, a1, etc., a k minus 1 just with a cycle. Yeah, you just run a cycle which outputs it. Then you output x, and then you output with another cycle all elements from ak to a n minus 1. What I did was use this approach. So I just take this as a vector of integers in C++, and there's a function, there's a method insert, which takes an iterator and an element. And as an iterator, I want right here the future iterator of x. So easily you can see that the future iterator of this element will be a begin plus k. Yeah, because each will be the next, the future kth element in zero indexation. Therefore, I just write here a begin plus k, and this works. Basically, that's it. Okay, problem B. Problem B. Intersection of cuboids. So there are two parallelepipeds, rectangular prisms, you can say. And we want to understand if they intersect or not. Well, in terms of, in the case of cuboids, there is a known fact that actually the two intersect if and only if. So actually, what I want to say, any cuboid is just a Cartesian product of some sets. For example, this cuboid is a Cartesian product of this subset of R, this subset of R, and this subset of R. Yeah, so simply first cuboid is just a Cartesian product of three different things. And the other cuboid is also a Cartesian product of three different things. Well, actually, in the case of Cartesian products, it's easy to calculate their intersection. It is simply the Cartesian product of intersections. So if you want this to have a positive volume, you want this to have a positive volume. And in order for this to have a positive volume, you want all of these sets to have a positive length. Yeah, because the volume of this thing will be the volume of this thing, and it will simply be the measure of A intersect D times the measure of B intersect E times the measure of C intersect F. So if you want this to be positive, you just want all these three numbers to be positive. So what is A? A is simply a segment on an R, and D is also, this is A and this is D. So A and D are two segments. So now you basically want to understand, is it true that two segments have a non-empty intersection? Not non-empty, but with a positive length. Yeah, so now you have a problem. You have two segments, L1, R1 and L2, R2. You ask yourself, is it true that their intersection has positive length? Well, this is quite standard. You just want to check that R1 is greater than L2 and R2 is greater than L1. If this is true, then you're good. And because the intersection is simply maximum of L1, L2 and minimum of R1, R2. So you want this to be less than this. This is the criteria. So you check all three conditions and take their conjunction. That finishes the problem B. So we go on with problem C. You are given a sequence A of length n. We need to choose exactly k elements from A and remove them, and minimize the maximum minus the minimum of the residual sequence. Okay, let's firstly sort our sequence. So let's say that A1, A2, etc. AN is the sorted sequence. In these terms, so if we remove some elements, then the minimum of the residual sequence is just the leftmost non-removed element. And the maximum is the rightmost non-removed element. Okay? So notice that you always want to remove several first elements and several last elements. Yeah? Because assume that you didn't. So this is the leftmost non-removed element. This is the rightmost non-removed element. And assume that you, for some reason, removed something from here. Well, in this case, you were unoptimal, because instead of removing this element, you could keep it and instead remove this element. This would, in the best case scenario, this would decrease the minimum, yeah, because it was like xi minus xj, and now it's xi minus xj plus 1, yeah, because this element is removed. Or not plus 1, but plus something. In the worst case scenario, it does not change, yeah. For example, if this element is equal to this element, then the removal of this one does not change much. But still, if there is an answer, if there is an optimal answer, there is some optimal answer. If there is some optimal answer, then there is some optimal answer in which you only removed several first elements and several last elements. Okay? So now the question is, what is the best answer if you remove several last elements and several first elements? So since you have just your array sorted, if you know the number of the first elements or the last elements, this is easy. For example, let's assume that you know that you removed I first elements. Then you definitely, let me just re-index it. So this starts with 0 and ends with n-1. So if you removed I first elements, then you definitely know that you removed k-1, k-I last elements. So what is the minimum after this removal? So the minimum is simply AI, yeah, because elements A0, etc., AI-1 are removed. What is the maximum element? So since you removed these number of elements, you know that AN-1, AN-2, etc., AN-K-I, they are all removed. So now the maximum element that you have is n-k plus I-1. Now you just need to subtract them. And this is your difference. But this is if I is fixed. So you know the answer when I is fixed. What is the answer if you don't know the I? You can simply iterate from 0 to k and minimize the answer among all choices. That's basically it. So there is a linear, there's a solution which firstly takes n log n to sort this array, and then it is simply a linear solution after that. Okay, problem D. Problem D. You have a string which consists of the following. It has some B's and W's, and in the end it has two like spaces, two empty slots, and the other string of the same format. You want to somehow transform this into this by doing the following operations. You take two consecutive symbols and put it there here. So now here we have two spaces, and here we have two characters which we borrowed from here. We can do this as many times as we want, as we want, yeah. And we want to get this string in the minimum number of steps. Okay, so actually how to solve this problem? This is a simple BFS problem. What is our state? Our state is, first of all, which string we have here. Actually, in the easiest manner, this is simply the string. There is something called BFS on arbitrary objects. Yeah, you just, if you have an object like t, then you need a q of t, and you need something like a set or an ordered set of visited objects, which can store t's and compare t's fast. However, in this problem, you could avoid viewing and setting over arbitrary objects like strings here. Instead, you can store this compactly. So you can just store the mask of all b's. For example, it's 0, 2, 3. So you store this number. And also you store the index of the first space. 0, 1, 2, 3, 4, 5. So you store two numbers, 13 and 5. So instead of this set, you have just a vector bool, a vector bool. Yeah, where the first dimension is this number, and the second dimension is this number. So how much do you need? So the mask takes 2 to the power 16 states, and the position of the first number, there are 15 possible positions. So you multiply by 15, and this is like around a million, probably. Not much. But also you don't, you not only do you need to store bool, you need to store int, I think. Because you want to store the distance from your string to the initial one. So you just run BFS over this set. You want actually ints. So you have the requirement to store a million ints, but you can actually store million ints. But the memory limit is enough for this. So in the BFS, you simply try to choose all pairs of consecutive letters, check that this pair does not intersect with this pair, and then you try to swap them. And then you check that this state is already propagated, and if not, then you add it to queue and update its answer here. Actually, very basic standard BFS stuff. So the solution is, what is the time requirement? So BFS works in V plus E time. So we need to understand what is the number of edges. The number of vertices is 1 million. The number of edges is kinda 1 million times 15 or 13, something like this, because for each string you have edges to all other positions of these two spaces. So something like this. Okay. This is fast, and this is enough memory. So simple BFS problem. Problem E. Okay, so what do they say? They say that you have a tree, a weighted tree, and you want to start somewhere and visit all edges or all vertices. I forgot. All vertices. So you want some route to visit all vertices. Okay, you have visited all vertices. Let's assume that we ended somewhere. Let's say that we have some route which visited all vertices. And let's say that its length is this. So we started in some vertex A, we ended in some vertex B. Let's also, in the end, go from B to A. There is the only route from B to A in a tree. So let's take route and then go BA. So now you have a Hamiltonian route in terms of not Hamiltonian, but it's like a cycle, yeah, because you ended where you began. But actually, you can notice that you have visited all edge, because if you did not go through some edge, then you couldn't visit the vertex which was on the other side of this edge. Yeah, for example, if this is edge, if this is an edge, then this is your side of vertex and this is other side vertex, and you couldn't visit this vertex without going through this edge. But also, since you ended where you began, you had to go twice along this edge. So root plus BA actually goes twice along each edge. So this is at least 2 times sigma, where sigma is the sum of all edges. Okay, therefore you can say that mu of root is at least 2 times sum of all edges minus mu of BA. So if you want to minimize this. Let's try minimizing this first. Yeah? And in order to minimize this number, you want to maximize this number. So you know that mu of BA is just the length of some path. Let's take the maximum possible path, which is diameter. So we definitely know that this is at least 2 sigma minus mu of diameter. Diameter is the longest simple path in a tree. Therefore, you always know that mu of your root is at least 2 sigma minus diameter. Actually, this estimate is precise. So actually, you always need exactly this many. This is the minimum cost of any Hamiltonian path in a tree. How to prove it? To prove it, you need to present an actual Hamiltonian path with this mass. To do that, let's find first the diameter of our tree. And now let's notice that if we have only these vertices as our tree, then indeed the mass is 2 sigma minus mu of dm. Because actually sigma in this case is equal to dm. So this is just mu of dm. Okay, now let's add some other vertices. For example, we have some vertex which was not visited. Let's find the nearest vertex in our tree to this vertex. So there is some path here. Now let's insert into our path this piece where we go from this vertex C here and immediately go back. So now we have added some new vertices. So this sigma is increased, and as much as it was increased, twice as much we have added new edges to our path. Now let's again take any vertex which is still not visited. Let's take the nearest vertex in our tree to this vertex, which might be here, but it also might be here. And again we insert into our path this piece, where we go like this and then like this. Again, if we added some portion of total weight S of edges, then it is added twice. So actually it is added twice in here. Therefore, this formula holds, and when we add all our vertices, we have a complete Hamiltonian path of this weight. Okay, problem F. X equals a to the power of b. Okay, so let's say that we have several sets. C1 is actually I did something stupid. Okay, never mind. C1, let's say that, okay, we have all numbers from 1 to n. Let's call this thing I. Let's say that Ci is the condition of being a complete ith power. So this is the set of all numbers x to the I, where x is a positive integer. And let's say that I is Ci intersected with I. This is what we want. Our goal is to calculate this set. Our goal is to calculate I2, I3, I4, etc. The size of this set. Okay? This is our goal. How to solve this problem? First of all, notice that 1 is included in all i's and in all ci's. Therefore, let's ignore that there is 1 here. So let's say that x should be at least 2. And instead, in the end, we add 1 to the answer. Sorry. Instead, we add 1 to the answer. So let's ignore that there exists just number 1 or number 0 or anything else smaller than 2. So now we have the problem where here we have 2. Let's forget about 1 for now. Okay, now actually you can say that the minimum number in Ci is not 1. It is what? It is 2 to the power I. This is the minimum number in the set Ci. Since this is the minimum number in the set Ci, sometimes it can be bigger than n actually. Yeah, for example, if I is at least 60, then this minimum is at least 2 to the power 60. But notice that n is actually at most 10 to the power 18, which is less than 2 to the power 60. Therefore, i's, the numbers i's, which are at least 60, are not interesting for us. We can ignore them. Because, so actually, all sets starting with I60 are empty. So this is empty set, I61 is an empty set. Yeah, Ci is not empty, but when we intersect it with numbers from 2 to n, it becomes empty. So now the problem is easier. The problem is calculate this. Okay, so we need to calculate this. The first approach that you might try is to simply calculate like this. So the size of I2 plus the size of I3 plus the size of etc. 59. Unfortunately, this does not work because these unions are not disjunctive. So some of these elements, some of the sets might intersect, and usually they will intersect. Therefore, if you have some element x, for example, which is both in I13 and in I5, in I13 and in I5, then you calculate it 2 times, and actually 3 times because you also will calculate it in I15. This is poor. So we need to somehow avoid it. Let's explore how we can avoid it. Let's explore how we can avoid it. We need to understand several things for that. First of all, we can understand that IA is a subset of IB if B divides A. Okay? For example, I6 is a subset of I2. Because if some number is a 6th power, then it's definitely a 2nd power and a 3rd power. Therefore, you're kinda not interested in composite numbers, composite indices. Let's just ignore for now all composite indices. We only want a prime indices. If we have some composite index like 24, then all its elements are already in I2nd. If there is, for example, I27th, we're still not interested in it because all the elements of I27th are also in I3rd. So if you have any composite number, you can replace it with its prime index and you're still in this set. So basically, let's ignore all composite indices. So now we'll have this problem: I2, I3, I5, I7, etc. I59. Still, unfortunately, these sets can intersect. Then you can improve this fact that IA is a subset of IB, where B is B divides A. And actually you can say that IA intersect IB is always I of least common multiple of A and B. Because a number is an exact 8th power and exact bth power of some number if and only if it is an exact this power of some number. Yeah, how can you prove it? So let's take some number x, which has some prime decomposition into primes. So what does it mean that it is an 8th power of some number? This means that actually A divides all alphas. What does it mean that it is a bth power? It says that B is also a divisor of all these alphas. And this is true if and only if this LCM is a divisor of all these alphas. Therefore, actually, this is true. Okay? But this means that we can apply inclusion-exclusion principle. So always when you have some when you have several conditions, let me call them D, for example. When you have several sets, you can apply exclusion-inclusion principle and calculate the size of this set. First of all, you need to add all the sizes of these sets. Then you need to subtract the sizes of their pairwise intersections. Then you need to add the sizes of 3-fold intersections. And etc. And in the end, you add or subtract the total intersection of all sets. Okay, so this is our exclusion-inclusion formula. What's interesting about it is that in the case that we have some sort of primes and products of these primes, the inclusion-inclusion principle starts working very nice. What do I mean by that? So notice that okay, let me rewrite it very compactly. So in a very compact manner, this can be rewritten like this. So we take sum over all non-empty subsets of indices then you take -1 to the power size of I minus 1 and multiply it by the size of intersection of the i's where I from I. Something like this. So this is in compact form. Okay? Now notice what happens in the case of our thing with primes. So as I said, the intersection of several i's, let me just rewrite it as it is here. So sum over all j's which are subsets of 2, 3, 5, 7, etc., 59, non-empty, -1 to the power j minus 1 times the intersection of the i's where I in j. Okay? Let's remember what I said about the intersection of these i's. Sorry, not di, but ai. Let's remember what I said about this fact. So actually, the intersection of two i's is the I with the number LCM of a and b. Therefore, here we can rewrite it like this. So this is minus 1 to the power j minus 1 times the size of I with LCM of all j's. And since all numbers in J are just different primes, then instead of LCM, we can write here the product of them. Product of J. Okay? So, to find the answer, we need to take all possible subsets of J and take minus 1 to the power J minus 1 and multiply it by the size of this set. What's interesting about this is that instead of iterating over all possible subsets, let's iterate over all possible numbers which are taken here. So let's call this number, I don't know, m. So first of all these numbers for all these different choices are different. Yeah, because any two different numbers have different prime factorizations. So m is just from 2 to infinity. Or for example, subsets of this thing, never mind. So first of all, we have im. Also, we need to multiply it by this thing. This thing is just what? What is this? So if m has at least two occurrences of the same prime, then we need to ignore this number m. Yeah, because here we cannot take 2 3 times. We can only take it 0 times or 1 times. But if we took it, then each new prime inverses the sign of this thing. This is called a Möbius function. It's actually denoted as mu. In this case, it should be minus. Never mind. So the sum of im times minus Möbius function of m. That's it, actually. And now, as I said, we can stop it at 59, because if we go on when it's at least 60, then, as I said, here it becomes empty. So all i's with big indices are just empty. So we can ignore them. So here we can actually stop at 59. So now the problem is iterate from for m from 2 to 59. For each of them, calculate Möbius function, which is minus 1, 0, or 1. And if it is not 0, so this is minus 1 or 1, then you can also you also want to calculate im and add it to the answer. So this is the problem. Yeah, so there is no infinite sum anymore. We just stop at 59. Okay, how to do it? How to do it? We only need to calculate im actually. So im is intersection of 2 etc. n and set of all i's that okay, set of all x to the power m's. Well, actually, this intersection is simply 2 to the power m, 3 to the power m, etc. at some number t to the power m. And the size of this intersection is t minus 1. Yeah, so if you have maximum mth power here is t to the power m, then the size of this intersection is t minus 1, because here are these t minus 1 numbers. If we also had 1 to the power m, there would be t of them. But as I said in the beginning, we ignore number 1. So we want maximum number t such that t to the power m is at most n. This is what we want to calculate. How to do it? So the easiest way would be to take power of t to the power 1 over m, and that's it. Yeah, because t should be at most mth root of n, and here we just calculate it. Yeah, in the end, we need to take its floor. And this would be right if all the calculations were precise. So if this calculation was precise, then actually you would get a correct number t. Unfortunately, calculations are not precise. It's possible that the true value of this number of this formula is 13, but you would get 12.99999 and a lot of 9s, 84, for example, I don't know. And because of that, you get an incorrect answer. So we need to fix that somehow. I decided to fix it that way. I take the ceiling of this power, and this is some number t0. And then I try to decrease number t0 while I still have... So our pseudo algorithm works like this. So t0 is the ceiling of n, of mth root of n. Then while t0 to the power m is still greater than n, we subtract 1 from t0. And then in the end we return t0. So this is the algorithm of finding that value of t. So this step is not required to give the exact value of this ceiling. So maybe it might be like +1. If it's +1, for example, it's fine. -1 is, I guess, impossible. Yeah, I think -1 is impossible, simply. So this can only be greater than the correct answer. Then, while this is true, we subtract this. And the only question is, how do we do this? Because you know, this exponentiation can lead to an overflow. So this is done in doubles. This is fine. But this is done in integers. So t0 to the power m can easily be greater than 2 to the power 64 and exceed long. Well, to prevent that from happening, there are two ways. First of all, you can just do it in 2 to the power 128, and if at some moment while calculating this stuff you exceed this number, you just stop. So it's easy to understand if your calculation has exceeded 2 to the power 64 in the process of calculating this power, and you can simply stop instead of continuing and getting an overflow. I used another approach. So I need to check that t to the power m is greater than n, where all these numbers are int 64s. And this is actually something like this. So first of all, I approximately check this condition. I approximately check this condition. So I just do it in doubles. So I use double t, double m, I calculate this power, and I compare it with this number. So if this is true, approximately true, then definitely, not approximately, but exactly, it is greater than n. Because if it is smaller than n, then in doubles you would get that this is false. Yeah? What do I mean by that? So t to the power m, in our C++ function, it said that it is greater than n times 1.01. This means that actually t to the power m is greater than n times 1.01 minus epsilon. Because there can be some errors. But the errors cannot be such big that epsilon is 1%. For example, it's definitely bigger than n times 1.009. Therefore, definitely t to the power m is greater than n. And so you have checked this solution, this condition. You know that it is true, because you know that even this is true. Okay, this is the first thing that we checked. Let me write it somehow structurally. So how to check that t to the power m is greater than n? First of all, we check in double precision that t to the power m is greater than n times 1.01. If true, then of course t to the power m is greater than n. Okay, now let's assume that it is false. This condition is false. Then we can simply say that we now check t to the power m is greater than n in integers. And now we can do it because we know that there will be no overflow. If there would be an overflow, that would mean that t to the power m is greater than 2 to the power 64. But if this is the case, at least, then definitely 2 to the power m is greater than n times 1.01. Yeah? So if t to the power m is at least 2 to the power 64, then obviously t to the power m is greater than n times 1.01, as it's written here. So this is impossible, and we can just do it in integer 64. That's basically it. And in the end, don't forget to add 1 to the answer. Finally, problem G, Go territory. This was pain in one place. So let me just briefly explain what I did. So first of all, we know that all what is happening happens in this square from 0 to this number. Let's extend it by 1 and add this frame. So add 1 to all coordinates, and now we leave from 0 to 2 to the power 10 to the 5 plus 2. Okay. Now we have something. Now what I want to say? Let's call a cell a point free if from it we can reach the frame. The frame is definitely free. We want to calculate the number of unfree points, which are not filled with a stone, but still you cannot reach the frame. This is called frame. So how to do that? Let's take any point. And let's go up until we either go into a frame or go into a stone. So if we have gone into a frame, then it is definitely free. Also, if you go down and see a frame, then also you are definitely free. So if everything is bad, then on top and bottom of you, you have two stones. Okay? Actually, let me put it another way. Let me put it another way. Let's forget about these two cases. Always, you just take a point, you go down, and either bump in a frame or in a stone, and you go up and bump into a frame or in a stone. What you want to say is that for all these points, the state of being free or not free is the same, because they are simply reachable from each other. Therefore, let's just say that we compress them into one somewhat vertex. So this is one vertex. So vertex can be, first of all, vertex has a length, which is the number of points in this vertex. Vertex, firstly it has length, which is the number of points in it. Secondly, it can be free or not free, which is it reachable? Is it true that from it you can reach the frame? Also, two vertices can be adjacent. Vertices are adjacent if you can get from one to another by at most one move. So the only way for two vertices to be adjacent is that they are in adjacent columns. So this is in column C and this is column C+1. And their segments intersect. This is the only way. It is easy to check if two vertices intersect or not by simply considering these two segments and checking if they intersect or not. Also, the number of vertices is like C plus n, something like this. This is the number of vertices, where C is the number of different columns and n is the number of stones. Maybe less. So this is like linear in the size of the input. Let's see. Okay, since this is true, and the number of edges is also linear, because like you can just list all edges by iterating over all pairs of consecutive columns and using two pointers to keep track of all intersecting segments and adding these edges. So now you have a huge graph. For each vertex you have its length and you have the fact that it is free or not. For some vertices which are adjacent to some frame, it's obvious that they are free. Yeah, so if one of the endpoints of a vertex is a frame, for example this one, yeah, this vertex is automatically free because it has one of its endpoints in a frame. Then evidently it is free. For some vertices, however, it is not so evident that they are free. For example, if we have these two stones, then it's not immediately obvious that this vertex is free. However, it is free because you can go left, and now there is this big free vertex. This is why we need these edges which connect the vertices. So as I said, the edges can be found via two pointers method. So we construct our graph in which some of the vertices are free and some of them are initially free and some of them are possibly free, possible not. We need to understand it by some sort of DFS. So you run a DFS in this graph, you find all connected components in our graph. So in each connected component you need to check, is there at least one free vertex there? If there is, then all vertices are free, and you just ignore this subgraph. If at least one of them, if none of them are free, then actually all these vertices are not free. For example, you can draw something like this. Yeah. Some spiral. Yeah, so there are several vertices. This vertex, sorry. So this is a vertex. This is a vertex. This, 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 and this. So they all form a connected component. Because these are adjacent, these are adjacent, these are adjacent, these adjacent, 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 adjacent. And none of them are initially free because none of them is adjacent to a frame. So basically you say that they are all not free. And then you just add up their lengths and add it to the answer. And so you get your answer. So the implementation is a bit heavier for me, at least. For some people it was 9 minutes, but for me it was a bit heavier. But still I managed to do it. So I'm glad to have done it, basically. That's it. Thank you for watching.